Hello everyone, this is Feiran from Osaka University. On behalf of all the co-authors, I would like to present our work titled Generalized Shuffled Linear Regression. This is a joint work between Osaka University and Line Corporation. Our project is already open sourced online and you can easily reach it by scanning the QR code on this slide. First, I would like to introduce the basic concept of the terminology shuffled linear regression. In the conventional ordinary linear regression with Euclidean norms, we have some input A and output B. These data are always given in pairs so that we know which certain A corresponds to which certain B. So, we only need to estimate the regression variable x by minimizing this objective function. On the other hand, in the shuffled linear regression problem, we consider the condition where the data undergoes an unknown permutation, like this. And therefore, apart from the regression variable x itself, we also desire to recover the matches between the data, which we characterize by the matrix P and call it the correspondences matrix. Then the objective function looks like this. Given the matrix P representing the correspondences between the data A and B, now let's see what constraints it should satisfy. Let's consider these two-point sites as an example. Say the circles are data A and the pentagons are data B. Then, intuitively, we desire that any pairs of AI and Bj to be either matched or isolated. As a result, we want the element of the correspondences matrix to be binary. Moreover, per the properties of a linear function, we know that each AI should match to exactly one Bj among all the possible candidates, and vice versa for B. That is, we desire the matches between A and B to be a bijective mapping, which can be realized by constraining the sums of each row and each column of P to be exactly 1. And in fact, these binary and bijective constraints imply that P is a permutation matrix, which is square and full rank. There, however, exists a severe limitation of such a vanilla shuffled linear regression formulation. That is, it forces every piece of data in both A and B to have a match. So, shuffled linear regression actually treats all the data as inliers. To be more specific, even there do exist some outliers which should in fact be rejected, like the A6 and B6 points. Then, the bijective property of P will keep assigning them a match. That is, the full rank and square correspondences matrix in shuffled linear regression would force to match to outliers. In this work, we propose a generalized version of the vanilla shuffled linear regression problem to mitigate its limitation on handling outliers. In our proposal, we keep the objective function unchanged and realize robustness by modifying the permutational constraints on the correspondences matrix P. First, we inherit the philosophy of shuffled linear regression that a pair of data should be either exactly matched or completely isolated. Hence, we still let P to be a binary matrix. However, different from the vanilla version that requires each row and each column of P to sum to 1, in our proposal, we replace the equality constraints by the less and equal one. That is, we no longer require every piece of data to have exactly one match. Instead, we say that it can either have a match or be completely removed from the matching process. However, these two constraints themselves are not enough, since there is a trivial solution by letting P be all zero. And therefore, we also introduce another constraint. That is, we fix the number of inliers to k, which is another unknown parameter that can be either manually set or automatically estimated by robust estimation techniques. And hereafter, let's denote these constraints by the letter pi for convenience. To solve the generalized shuffle linear regression problem mentioned in the previous page, we also come up with a very simple yet effective optimization algorithm. Our proposal is based on a key observation that the original objective function can be reformulated into a weighted least squares manner if we consider all entries in P as weight coefficients. Then, given this reformulated objective function, by applying alternative optimization on it, we can see that optimizing X with P fixed is simply a weighted least squares problem, which should be globally solvable in most cases. Moreover, if we fix X to optimize P, this in fact leads to a k-cardinality linear assignment problem, which can be converted to an ordinary version in square time and then solved by the Hungarian algorithm globally in cubic time. And finally, by fixing both P and X, we can easily estimate the number of inlayers K as an estimator and update it via robust estimation. One may have already noticed that our proposal is pretty similar to the famous ICP algorithm for point cloud registration and its robust variance. However, there is a key difference that ICP-style algorithms cannot guarantee an 1-to at most 1 correspondences due to its nearest neighbor-based matching strategy. For example, by searching for the nearest neighbors on the first standard solve for both points P1 and P2, we get P1-. Such a result is counterintuitive since we know that 3D spatial transformation cannot map a single input to two outputs simultaneously. On the other hand, shuffled linear regression and our generalized version do not suffer from such a problem due to the 1-to at most 1 constraints. Moreover, if we keep finding correspondence for P3, both the vanilla permutational constraints and the nearest neighbor-based searching strategy would match it to P3-, which is a wrong result since it is in fact an outlier. On the other hand, our generalized shuffle linear regression won't suffer from such a problem. Applications of our proposal exist in broad fields, especially in geometric computer vision. For example, for the image registration task, by treating the data A and B as the homogeneous pixel coordinates of the feature points, we have the regression variable h characterizing the homography matrix. And here are the results. On the source and target pairs, green lines are the in-layer matches detected by our proposal, and the red dots are identified outliers. As shown, our method provides almost the same results when visually compared to the ground truth. On the other hand, the vanilla shuffled linear regression shows obvious distortion due to the existence of outliers. The second task we carried out is point cloud registration. In this task, the data A and B are the homogeneous coordinates of the 3D point clouds, and the regression variable t is the spatial transformation. We present two setups in the slide. More results can be found in our paper. For the first one, we contaminated the bunny point clouds with outliers. This one shows the initial poses of the 2 point clouds, and this one records the result achieved by our proposal. The dark blue points here are the outliers detected by our algorithm. The lower figure depicts another setup, in which we want to register 2 point clouds that are partially overlapped. As we can see from the head and tail parts of the dragon, our result is obviously better than the other peer methods. With the point cloud registration setup, we would also like to demonstrate the importance of maintaining a permutational matching. Specifically, we register 2 outlier contaminated point clouds under varying initial rotations. Let's first see the result from the robust version of ICP, the trimmed ICP algorithm with a 50% trimming ratio. As shown, well-trimmed ICP can present good results given a reasonable starting point. It appears to be very sensitive to initializations. On the other hand, Our proposal can tolerate much higher initialization errors compared with the trimmed ICP algorithm. Given the fact that both of these two algorithms are sharing pretty similar techniques for robust estimation, we can see that constraining the matches to be permutational do helps, making the performance more stable. The third task we have carried out is isometric shape matching, which aims at recovering the vertex-wise correspondences between two isometric meshes. In this task, we follow the functional map pipeline and retrieve the data A and B from the Laplacian Boltzmann operator. The upper right image shows an example error map. The warmer the color, the larger the error. The leftmost figure is the source, and the rightmost figure is the result achieved by our proposal. Matched vertices are painted with the same color. We also evaluated the ability of different methods on preserving bijective correspondences. On the bottom right image, we mark out vertices which are mapped to more than one target. As shown, our method can maintain an obvious higher ratio of reasonable matches than the counterparts. Thank you for your listening. If there are any further questions, please feel free to reach us via the QR code.